Hello everybody, this is task 2 for fundamentals of computer systems. In this task we are going to discuss the storage elements in a computer system. This is our second task. At the end of this task you are going to have a test which will be available on SULMS. So the task again once more, it is the computer storage elements. So how the task goes, we are going first to discuss the registers. What are the registers? What type of registers we have? Then cache memory. We heard about cache memory. What is cache memory? And why do we need cache memory? Then random access memory, which is RAM. You all know RAM. And read-only memory, which is ROM. So we are going to discuss all of these in this task. So first of all, we need to know memory access methods. Memory access methods is the way that we access the information inside the memory. The first type is the sequential type. Sequential type, keep in mind, it's just like this tape over here. In sequential type, the access starts in order, meaning if I want to go in a specific place in the tape, I need to go through all the tape, then go to that place. So access time depends on the location of the data. Now this was used early in early computers, and now after that was famous for cassettes, tapes, and VHS videos. The next type is the direct memory access, direct access memory, which is having addresses of unique blocks in the magnetic tape. And an example is the floppy disk and CD-ROM. So the access time is by jumping to the vacant plus the sequential search. So the access depends on the location of the previous location. Now, just keep in mind, tapes are very slow. Floppy disks are much more faster. After that, we have the random, which is called random access memory, where access time is independent of the location. So we have a uniform access time wherever we want to get a location, we will get all the time the same time for accessing the information. And example is the RAM. Same examples nowadays, although it's random, we have the SSD drives and flash memories, they depend on random, but mostly we know random in random access memory, which is the RAM. The last type is associative, and this is a special type of access which is used by cache memory. The access time is independent of the location of the previous access, which makes cache memory quite a fast memory to use. Now, next is the memory hierarchy. What do we mean by memory hierarchy? Now, memory hierarchy is like a pyramid, اللي هو هرم. Now, the pyramid, on top of the pyramid sits the CPU. Why on top of the pyramid sits the CPU? Because it is the fastest. So, on top of the pyramid is the fastest memory or fastest speed. Registers, which are part of the CPU. If you recall, in the previous task we talked about the CPU, and we said that the CPU consists of three things. Do you remember them? They are the control unit, arithmetic and logic unit, and registers. Registers is the memory inside the CPU. Its speed is the same as the speed of the CPU. Next, we have the cache memory. Cache memory sits between the registers and the RAM. Okay, cache memory sits between the registers and the RAMs. So this is our cache memory. Cache memory is faster than RAM, slower than registers. Then we have the RAM, which is random access memory, which is our main memory. We call it main memory. RAM is the main memory. So we call the RAM main memory. Next, we have the secondary storage elements, which are the ROM, removable drives, network instant storage, and hard drives. These sit just below the RAM. And finally, in the base of the pyramid, we have the slowest memory components, which are keyboard, mouse, removable media. All of these are considered the slowest in terms of speed for the CPU. So registers, L1 cache means level 1 cache, level 2 cache, main memory, which is the RAM, then cache disk, optical, and tape, and so on. So this hierarchy depends on, once more, speed. Next, we are going to talk about registers. Why do we need registers? We talked earlier in task 1, and we said that inside the CPU, you need some sort of memory to hold the data for intermediate operations. Let's say I'm going to add A plus B. Where am I going to store the result? If I'm going to use the results once more, I'm going to store it in the registers. Where am I going to get A and B? They will be stored also in the registers. So registers are part of the CPU, and they are on top of the memory hierarchy. Their speed match the CPU speed. They are large in size and consume significant power. This makes the number of registers small. Why? Because they are large and consume a lot of power. What's the problem with power? What's the problem with power? Consuming power means heat. Heat is not a good thing for electronic devices, and so for that we cannot put a lot of registers. So they are small permanent storage locations within the CPU. They are used for particular purpose. Each register has a particular purpose. They are manipulated directly by the control unit. What do you mean by manipulated? Manipulated means they are controlled and their values are changed through the control unit. Registers are wired for specific functions, which we are going to see later in the next slide. We are going to see that we have registers for specific functions. Size, bits, or bytes. Mainly, if your CPU is running a 32-bit operating system, then your registers will be 32. If you are running 64, it will be 64 bits. Later on, when we go and talk about microprocessors and microcontrollers, we are going to talk about registers of different sizes. We are going to talk about 8-bit, 16-bit, 32-bit, and 64-bit registers and how to manipulate the data in them. So they can hold data, and an address or an instruction, meaning any data that is needed inside the CPU will be stored inside the registers. We have two types of registers, general purpose and special purpose. General purpose registers, these registers are user visible. Once we start programming in assembly language in level 3, we are going to program the CPU using these registers. They hold intermediate results of values, loops, and counters, typically several dozens in current CPUs. Now, general purpose registers are for the users to program and to use for their manipulation. The second type is the special purpose registers. Special purpose registers they have a specific purpose. Okay, each one of these has one job only. For instance, program counter, it holds the address of the instruction that is going to be executed next, or sometimes we call it instruction pointer. Then we have the instruction register, which holds the currently executed instruction. Then we have memory address register. If we want to put an address on the address bus, then that address should be stored in the memory address register. If we want to put a data on the data bus, then that will be stored in the memory data registers. Finally, we have the status registers, or we call them the flag registers. They hold the status of the CPU and currently executed program. What do we mean by status of the CPU? Let's say I added two numbers and the result is a negative number. Then we have the sign flag as 1. Let's say we subtracted two values and we had the result as 0. The 0 flag will be 1, and so on. We have special purpose registers which are used for that purpose only. Now, when we talk about memory, how do we go around memory? How do we understand memory? Each memory location has a unique address, meaning we have a memory. Each memory, this location, has one address, which is 000. The next one is 001, and so on. Now, in order to do that, we have the memory address register, which we talked about over here. This is the memory address register. we have the memory address register and the memory data register. We put the address on the memory address register, then a decoder will decode this address and activate a particular cell which will send the information to the data register. All of this is controlled by the CPU. CPU controls all of these information. Now, memory data register is a two-way register. Memory address register is a one-way register. What do we mean by that? Memory data register, we can store in the memory and read from the memory. We can read and write into the memory. So we can send input and take output from the memory data register. On the other hand, the memory address register takes information in one way from the CPU. You cannot have it two-way like the memory data register. So keep this in mind. Memory address register one-way, memory data register a two-way register. Next comes the cache memory. Now, the cache memory, I don't know if you heard about it, but cache memory is quite an important memory. In every CPU, you are going to have a cache memory. Let me show you something. So if I go on my computer over here and I go for my task manager. On my task manager, you can see if I go here more details and I will go for performance. You can see here, this is my CPU, everything is running fine. You can see that I have level 1 cache of 256 kilobytes. It's a small memory. Level 2 cache is 1.0 megabytes and level 3 cache which is 8 megabytes. This is a i7 8th generation processor. So it has 3 cache levels. Okay, 3 cache levels. So why do we need this cache memory? Okay, why do we need a cache memory? The basic idea is the CPU is very fast. It's running on gigahertz, which is 10 to the power 9. Main memory, so this is around 10 to the power 9 of speed, frequency. Main memory is running around around megahertz. Okay, so this makes the CPU much more faster. Mega, which is 10 to the power what? 10 to the power 6. Okay, so this makes the main memory very slow compared to our CPU. This will make a bottleneck. What's a bottleneck? Bottleneck بالعربي عنق الزجاجة. This bottleneck means that the CPU is asking for information, but the main memory is not having enough speed to give that information. Instead, we created what we call cache memory. Cache memory sits between CPU and main memory. So if I want data from the main memory, the CPU will put the address on the address bus. If it's in the cache, then the cache will bring it. If not, it will go for the main memory. You will say it's taking too long because I need to check the cache and then get from the main memory. Yes, but when we get the data from the main memory, we do not get 1 byte of data. We get a full block, meaning all the block of information related to that byte will be stored over here. So the next time you require a byte, most probably it will be available in the cache. This makes the cache very, very, very fast. So it's a small amount of fast memory. It sits between the main memory and the RAM. Its location may be on the CPU or outside the CPU, which we are going to discuss in the next slide. Cache operation. CPU requests information from the memory location. The CPU wants some information. Check the cache for data. If the data is present, meaning we have the information in the cache, okay, send it to the CPU and we get the information very fast. If not present, read the required block from main memory into the cache, meaning take the full block of information, put it in the cache, then deliver to the CPU. Now, once the block is available in the cache, you're going to, next time you need an information related to that previous byte, you will find it in the cache. This makes the cache extremely fast. Next is the evolution of cache memory. So in this slide, I put some information for you. You can see that the problem was the external memory is slower than the bus system, meaning the main memory is very slow compared to the CPU. So what they did in the 386, remember 386, I said x86, these are the 32-bit processors. So in the 386, they added an external cache using faster memory technology. So cache started over here. Then, although we added this cache here, increased processor speed resulted in external bus becoming a bottleneck. Yes, we added cache, but CPU is getting faster, cache is a little bit slower. So they said we have another problem. So the solution was move this cache, this one, move it on the chip, meaning inside the CPU we have one cache. Things also became we had problems. So internal cache is rather small. You saw earlier in my laptop, it's very small in kilobytes. So they said, okay, the solution, make a level 2 cache, which is an external memory. This is all in the 486. Now, everything was fine. However, we started having a problem because we have two types of information. We have instruction and we have data. So we need to access this information at the same time, and the cache was not enough. So they said, okay, create two separate cache, one for data and one for instruction. Sorry, this was presented in the Pentium processors. So after that, we have the Pentium Pro. Increasing speed of processor results in an external bus becoming a bottleneck for L2. So they said, okay, create a separate bus for the L2. And later on in Pentium 2, we still had the same problem. They said, okay, let's just move cache L2 onto the CPU chip. Now, in Pentium 2, that means that we have level 1 cache, level 2 cache are both on the CPU. Next was some application deal massive databases, so we had some problems. So in Pentium 3, they said, okay, create an external level 3 cache, and in Pentium 4, we moved that cache on the chip. So in Pentium 4, you have 3 caches, and all these 3 were on the CPU itself. So we have level 1, level 2, and level 3 caches. This is the Pentium 4 block diagram, which is over here. So in Pentium 4, we have level 1 data cache. Okay, we have level 1 instruction cache. So we have two separate caches for level 1, one for data, one for instructions. We have level 2 cache over here, and we have level 3 cache. Now you can see level 1, 16 kilobyte, 12 kilobytes. Level 2, 512 kilobytes. And level 3, 1 megabytes. So this is how things are running inside our CPUs. Our CPUs are very complicated, but most probably, or most of them, they run the same idea. So here you can see CPU contents. We have our register file, we have our ALUs, and of course we have our control unit over here. Next up is the random access memory. We know the random access memory, which is RAM. Random access memory, or RAM, provides large quantities of temporary storage. Now, we talked about RAM earlier in task 1, and we said that RAM is very important. For instance, if for some reason my phone is stuck or my laptop is stuck, I will restart. Why do I restart? Because basically RAM will be emptied and it will reload everything. Why? Because RAM is a volatile memory. Volatile means what? Volatile means power off the electricity, all the information will be lost. So RAM is similar to a memory, but it stores many values. The address will specify the location, and each value can be manipulated as one word, and each word depends on the CPU. It depends, either 32 bits, 64, depends. So we refer to memory properties as follows. We should be able to store many words, we should be able to read the stored words, and we should be able to change. This is the RAM over here. Now, how do we read and write from RAM will be discussed in the next slide. Here, just I want to show you how to think about RAM. Think about it as an array. Each location can hold one word, and each location has an address. So the address serves as an index, and each location can hold one information of data. So how do we read from RAM? This is the block diagram of the RAM. So the block diagram of the RAM shows the main interface over here. We have the address, which is K. It's of size K. We have the data, which is of size N. So we have 2K to the power N is the size of our memory. We'll be discussing this later on. So the address specifies the address. The data has the information. Out will have our information. Remember, we need to read and write. So in order to read and write, we need a WR chip, WR read write, and CS, which is chip select to enable this RAM. So the size of the RAM is 2K to the power N. K is the address lines. Don't forget this. So if I have K equal to 32, this means what? I have the size of the RAM 2 to the power 32, which is equal to 4 gig. We have discussed this earlier. Now, 2 gigabyte or bit depends on N. If N is 8, then it's 2 gigabytes. Okay, so for example, if I have 2 to the power 24 RAM, what is the contents, or how many bits I can store? It is 2 to the power 24, which is 16 mega words. 16 mega. How did I get 16 mega? It's 2 to the power 4 multiplied by 2 to the power 20. Okay, 2 to the power 4 multiplied by 2 to the power 20. So in total, I will have 24 address lines. The total storage will be 2 to the power 4 multiplied by 16, which is 2 to the power 28. How? 2 to the power 24 multiplied by 2 to the power 4, which is what? 16, which will equal to 2 to the power 28. للتذكير الأسس في حالة الضرب تجمع. Okay, الأسس في حالة الضرب تجمع. We will add the power in term when we multiply the numbers. Reading and writing from RAM. What is the process of reading and writing? So in order to read from RAM, okay, in order to read from RAM, first chip select is equal to 1, WR is equal to 0. Where did I get these values? From here. See, chip select is equal to 1 if you want to use the RAM. If you want to read, WR is equal to 0. Next, select the read equal to 0. Send the desired address on the address bus. The contents will be available on the output over here. If you want to write, on the other hand, same idea. CS is equal to 1. WR will equal to 1 over here. Compared here, it's equal to 0. Then send the desired address. Put the address on the data bus over here, and you can get your information. Next step is how to design a RAM. Now, we can use these cells to make a 4x1 RAM. 4x1 means what? Means I have 4 memory locations. Okay, coming back here, I have 4 memory locations. These are 4 memory locations, and each memory location can hold 1 bit only. So this is my bit holding module. This is a decoder. Anyone remembers what's a decoder? What does a decoder do? A decoder, let me add a slide here. Okay, a decoder am I recording? Okay, so a decoder, let me go back. Okay, a decoder will do what? Sorry, a decoder, the pin, if I have 2x4 decoder, 2x4 decoder, any decoder will have n multiplied by 2 to the power n size. It will have 2 inputs and 4 outputs. Inputs, I will call them I0 and I1. Outputs, I will call them A0, A1, A2, and A3. We discussed this in digital systems, but no problem, we can discuss it once more. So if the inputs I0, I1, and the outputs, oops, sorry, and the outputs are A0, A1, A2, and A3. Okay, so we have the inputs 0, 0, 1, 0, 1, 0, 1, 1. So, oops, again, I should do it like this from the right to left. Okay, so 0, 0 will give us 1, 0, 0, 0. 0, 1 will give us 0, 1, 0, 0. 1, 0 will give us 0, 0, 1, 0. 1, 1 will give us 0, 0, 0, 1. So you can see the decoder, only one output, these are our outputs, is active at any time depending on the inputs. Let's go back over here. So if I put on the address 0, 0, I'm going to select Q0. If it's 0, 1, I'm going to select Q1, and so on. Next step, this is a 4x4 design for a RAM. So this is our 4x1. So we connected another 3 modules to it, and all the connections are connected to the lines. You can see here, if we track, it's all in red. Let me change the color. Okay, if you see here, Q0 is connected to this one, and to this one, to this one, and to this one. The output, the inputs, data 1, data 2, data 3, and the outputs are down over here as output 1, output 2, output 3, as you can see. Enable, the full RAM has 1 chip enable and 2 address bits, and the WR, of course, for each module over here. Now, how can we design a RAM? I want to design a 256K RAM out of 64K. Now, the idea is, it's not always easy to find a 2x256 kilo RAM, but sometimes in the market you will find a 64K cheaper. So we are going to do a simple division. 256K over 64K, which will equal to 4. This means I will need 4 of these modules over here. Now, 64K is 2 to the power what? 2 to the power 18. Sorry, 2 to the power 16. Okay, let me fix this one. It is 2 to the power 16, so 8. Okay, once more. 64K is equal to 2 to the power 16. This means I will need 16 address bits for each one of these guys over here. So I have here 16 address bits, as you can see, address from 0 to 15. Type 256 is what? 256. Oops, I'm sorry again. What happened here? Okay, pen. 256 is what? It is 2 to the power k. Sorry, 256K is 2 to the power 18. So we have 18 minus 16. We have an extra 2 lines which are going to be connected to the decoder. What is the size of the decoder? 2 inputs, 2 by 4. So it's here 2 by 4 is our decoder over here. So this explains how we are going to connect the RAM, as you can see. If you want to expand, so if I have 64K, it means I need 2 64Ks connected beside each other. Now 16, my design needs 16, and here I have 8. 16 by 8 is 2. This means I need 2 of these over here. So over here, I'm going to need 2 connected in parallel. So to keep things in context, if you want to design a big RAM, you need to make sure how many RAMs you want to put in one module as one, as in parallel, or when we say as how many rows, and here's how many columns you want to put. In the solved exercises, I have put for you more examples on this. Next up is our read-only memory, and the read-only memory, as you can see, it's a little bit different. What's missing? You can see here is my read-only memory. What's missing? I have the WR not available, data not available. But why? Because it's a ROM. It's read-only memory. We don't need these because we have a problem. Sorry, we don't have a problem. We don't need them because we don't want to write anything. Okay, sorry, we don't want to write anything on the RAM. So ROM, sorry, on the ROM. ROM is a special kind of memory whose content cannot be modified easily. We only read the information from it. It holds the BIOS information, which is the startup information for any computer. And microcontrollers and all programmable chips, they have ROM. ROMs are basically the memory of devices that you don't want to change. For instance, you never program your remote control at home to do anything extra because the information is already stored inside the ROM. Your car keys, the remote control, you cannot reprogram them to do something extra because they are programmed for that particular task, which is the use of ROMs. Now, ROM is a memory which is basically information is stored like a table. So location 000 will have this information. This is an example. Location, so first location will have this information, second location will have this information, third, and so on. So basically it's a truth table like we studied in digital system. How do we design a truth table? The simplest way was using a decoder. Remember decoders, right? So if you remember in the course COMP2113, which is digital systems, we use the decoder to design the circuit, which is this circuit. Anybody knows what's this circuit? Yes, it is the full adder. Remember full adder? I'm sure you remember full adder. It's not easy to forget. Now full adder, 0 plus 0 plus 0, sum is 0, carry is 0. 0 plus 0 plus 1, sum is 1, carry is 0. 0 plus 1 plus 0, 1, 0. 0 plus 1 plus 1, 1 plus 1, sum is 1, carry is, sorry, sum is 0, carry is 1, and so on. We get this truth table. In order to implement this using a decoder, it's quite simple. This is my sum. My sum is high on 1, 2, 3, 4, and 7. So I go here for 1. You can see here 1, 2, 4, and 7. This is my decoder, and carry same way. Quite simple, straightforward. However, this problem, you see Q0, we did not use it. This makes designing using ROM quite an expensive design. So the ROM setup, you can create your ROM in this way. So going back to this example, okay, so I have 3 outputs and I want to design them. I have V0, V1, V2. So to do the design, we are going to put the values. Here is V0, V1, V2. This is sum of products. Remember sum of products in digital systems. Sum of products for V0, it is this value, which is 4, 6, and 7. So V0, 4, 6, and 7. So we draw the line like this. We put an OR gate and we put an X on 4, 6, and 7, and we do the same for V1 and V2 to make things easier or simpler. Instead of drawing 8 lines going down here, we just draw 1 line, and it's understood that it is an 8 summative OR gate. Next step is using programmable logic arrays, which is the commonly used method. PLAs is a programmable logic array. So the problem with ROM, it requires, for a ROM, it requires n to 2 to the power n decoder. So if I have my n equal to 8, I need a decoder which is 8 multiplied by 256. It has 8 inputs, 256 outputs. If I want my ROM to have 10 inputs, then it's 10 by 1024, and it becomes more complicated when you go for 32 and 64 bits. You need n inverters, 2 to the power n input AND gates. So if my gate is an AND gate, okay, if I'm using a 10-bit, then I need 1024 AND gates. Each AND gate has 10 inputs, which becomes extremely expensive. So to solve this problem, we use PLAs, or programmable logic arrays. Now a programmable logic array will have a size. For example, this array will have 3 by 4 by 3. 3 is the number of inputs. The other 3 is the number of outputs. 4 you can only find out once you finish your design. So let's go to our example over here. The truth table, which is this truth table, we fit it into a Karnaugh map, as you can see, and we solve the gates. In order to solve these gates, we find the summation. Now remember, we are not solving a normal Karnaugh map, we are solving all together. So if these two, you see these two are common. We try to find common values. Yes, if I was solving a normal Karnaugh map, I will connect these two together, but no. You see this one here with the purple square, it's matching this one over here. The one here in red is matching this one. That's why we did not connect this one and this one, if you recall the Karnaugh maps. After you finish your design, you are going to get your PLA in these values. This is the first one, the second one, third and fourth, and you get your design as you can see over here. Again, another example, solved exercise is available on SULMS in the solved exercises portion. Hope this explanation was straightforward. If anything is not explained, I'm happy to put more videos for you. You can ask on Microsoft Teams. I will be happy to answer you, and we can put more discussions on Microsoft Teams as we go. Now that's all. This is the references if you want to study the references or read the references. That's all for this task. Hope to see you soon. Stay home and stay safe, please.